You guys say? Yeah, like I respect
All right, good morning, everyone. So last class, we finished talking about capacitors, and we had a capacitor, well, I had this big capacitor up on the front table here, and we ended with a bang, right? Now let me ask you a question as we're going to transition to, we've been talking about conductors in equilibrium, and now we're going to transition to talking about when conductors are not in equilibrium, right? When they're not in equilibrium, that's what causes charge to move. Charge wants to move when there's an electric potential gradient. Okay, so here's this capacitor. Now, let's just say that the wire is not connected between the two plates. So the question I want you to ask, or the question I'm going to ask you is, first of all, does a capacitor store charge?
Yes.
Does a capacitor store charge? So, I guess there's only, this is binary, there's only two options, yes or no. Does someone need one of these? Extra one? All right, take a moment. I want you to try to convince your neighbor. All right. Does a capacitor store charge? And your vote? Well, it's actually not yes. It doesn't store charge. Why the heck? Why? So a capacitor. Now, why does a capacitor store energy? Right? Because it takes energy to separate charge. Whenever you want to separate charge, that's what takes energy to move, successfully move charge from one plate to the other. But there's no charge on a capacitor. Just like in a circuit, there's no charge. Circuits aren't charged, but their capacitor will separate charge, and that's where energy is stored. Okay, now, that's why we always have plus Q and minus Q. Naturally, the lowest energy state would be for those charges to go together. right? It would take work to pull them apart. Yes?
So how can it have charge without storing charge?
Well, there's no net charge, right? There's a one plate. This plate has excess electrons, right? And in fact, it's not really that many excess electrons. It may be on the order of nanocoulombs, right? Which is still several billion electrons, but really there's just, and where did it get those from? It got it from this plate over here. But there's no net charge in our system, but we've paid a price to separate those charges. And then the idea is now you can do something useful when you've separated those charges, and then that you can drive the flow of charge. All right, now, so given that we have this scenario right here, what would happen if we were to connect the wire here, or close the switch? The first question was charge on capacitor. So if I close the switch, what's going to happen basically? Charges stay on plate, or discharge through wire. Right? And let's just think about the reasoning for each of them. When the charges are on the plate, they're being attracted by Coulomb's force, right? The positive charges attract the negative charges. Now let's assume this is an ideal capacitor. An ideal capacitor is one where we're not considering the fringe field or how the lines will kind of bend towards the edge of the plate. Will the charge, when the charges are on the plate, they're being attracted by the Coulomb force. But if I close the switch, they could potentially discharge, travel through the wire to discharge the plate. Now, which one's going to happen? Okay, now, take a moment, and I want you to discuss with your neighbor here is, we looked at a non-ideal capacitor, right? We saw a spark, we saw a flash of energy being released. What about an ideal capacitor? What would happen if it was an ideal capacitor? Take a moment, explain to your neighbor what would happen. All right, so ideal capacitor, prepare your votes, A or B. Mostly B's, there's a couple A's. I don't see any C's because I didn't give you a third option. All right, well, this is actually kind of a bit of a tricky question, right? Now, if we were to think about this here in terms of what would cause charge to actually want to discharge through the wire, well, if we had a completely uniform field, all the charge is on the inside here of the plates. So I draw the electric field lines inside the capacitor. If we think about a charge that's sort of right here, there's no electric field over here to push the charge to make it move. How would it get moving? to even start the discharge process. In order for something to kind of kick the discharge process off, you would need something like a fringe field to start that process, and then as as one of those charges gets elbowed out of the way, then they can start to flow through the wire, right? So it's not entirely clear what would happen. So in an ideal capacitor, it's possible that charge would actually stay on the plate, but as we saw, a real capacitor, and this one, if I charge it up, now this one's wired to a light bulb. The light bulb is bright, and it gets dimmer and dimmer. About 40 or 50 volts. What am I at now? 60, 70, 80. Right now, if I bridge the two leads, get a rapid discharge and actually a heat release in the process there. So there was a rapid burst of movement of charge, or that process would be disequilibrium. Now, yes?
So it would discharge through the wire if it wasn't an ideal capacitor?
Correct, yes. So now that's what we're going to talk about, is discharging a capacitor. What's the process of discharging a capacitor? We want to think about why does the charge actually move. To begin with, well, first of all, let's just put a couple numbers on here that will sort of help us get an understanding of what's going on. Now, I drew a big fat conducting wire here, and what we could think of is right now this system for a real capacitor is going to be in equilibrium. So all the excess electrons, they're going to spread themselves out such that there is zero electric field on the inside, but they're going to kind of spread themselves out over the surface. The electric field is zero at all points, and we might be dealing on the order here of about 100 nanocoulombs. Okay, so maybe several billion or tens of billions of electrons. So why does the capacitor actually discharge? Well, as soon as I close, and then on this side right here, I can have some positive charge that kind of spreads out over the wire. Right now, as soon as I close the switch, right now there's a pathway for the charge to flow. Now, which charge is actually going to flow? Well, that's what we call the conduction electron. So there's going to be a whole sea of conduction electrons. Right, maybe around 10 to the 23 conduction electrons. So all this one, we want to imagine this plate and this wire as like a big pipe that's full of water. Right, and all we've done is added a little bit extra onto it here. So this one has a little bit of a higher pressure than that one, and it's going to basically, when you connect the wires, it's going to cause all the charge to shift a little bit. Right, but when I connect the plates, no electron from the negative plate is moving all the way over here. What's really happening is if I had a U-shaped channel filled with water and I put a drop in one end, it causes the drop to go out the other end. That's really what's happening when you close the wire. There's just a slight shift in that sea of electrons. So this is a pipe that's already completely full of electrons. They all just shift a little bit to neutralize the capacitor plates. So how does that actually happen? Well, what causes charge to move? Electric field. So as soon as you connect these two wires, you can see here that there's a plus here originally and there was a negative there. That's going to create an electric field. Right? Now, this one, this negative electron right here will be, in a sense, pulled really hard by that one because it's really close. But this one is, if this one shifts a certain amount, that one's not going to shift quite as much, but it's going to shift a little bit, right? So what we end up starting to see happen is, once you close the wire, is you get sort of a non-uniform distribution of surface charge. Okay, and this is the key point right here. It's the non-uniform surface charge which drives the current. Non-uniform surface charge sets up an electric field. If the charge is a little bit more dense here than it is right there, we're going to get an electric field inside the wire, which now starts to guide. So it acts like a field guide to guide the electrons through the wire. Or the electrons would move against the electric field here. Right? So all the charge is on the surface, but it's that non-uniform distribution which actually causes or pushes and pulls the charge and actually causes it to drift through the wire. And that process happens very, very quickly. Happens on the order of, and you saw how quickly it took to discharge. The discharge process was on the order of nanoseconds. Right? Because no one electron is moving all the way from one plate to the other. They're all just shifting a little bit to neutralize the plates. So this is now, for that brief nanosecond, that's actually very difficult to study that process, what's really happening in that 1 nanosecond. But that would be the process where it's not in equilibrium, right? Everything is shifting a little bit, and the system is not in equilibrium. All right, now, so let's try an example. Imagine that your wire is just a circular wire with a circular cross-section, and you're modeling that wire by a series of successive rings. So your wire looks like this, and you're basically slicing the wire into rings, right? So for instance, this ring right here, that section of the wire would sort of be like I have positive charge here, negative charge there, or I could even positive, negative, plus, plus, minus, minus. So it's a non-uniform distribution of surface charge. Okay, so now which of those following scenarios would give you a largest current? And we'll distinguish here between electron current and current, but which of the following scenarios would give you the largest amount of current? The following scenarios there. I'll give you a moment to prepare your vote. Okay, so you're working individually right now, so let's have a show of votes. All right, it looks like we have an agreement that D has the most electron current. So D is the most. So let's now, I want you to rank. D is correct. D has that, because there's the largest gradient in surface charge in D. So it would produce the largest electric field. Remember the electric field for a ring? A uniformly charged ring along the axis is just axial electric field. All right, so now let's rank them. Take a moment to rank from greatest to least. By the way, which one of these is going to be least? All right, take a moment, rank them from greatest to least. We know what the greatest is. D is the greatest, then just rank the rest of them.
E is equal to the right, C is 4 on both sides. E is 4 on the left. There's a number of how many plus signs we can
Are they like on there? Okay, I see.
All right. Now, does everyone agree with, and actually it may be a little hard, it might be a little hard to see that picture if you're kind of at the back there, but does everyone agree with that ranking? So whatever the charge difference between the two rings is the largest, that would create the strongest electric field. So really we have 4 units of charge difference here, from 2 positive to 2 negative, and here we go from 4 positive to 2 positive, so that's 2 difference, yes.
What do you mean by electron current?
Electron current. So current, and that's what we'll talk about next. Current is just the flow of charge. Okay, so basically you're just thinking about how much charge is actually, how many electrons would that basically cause to move. So remember, this pipe is full of charge, full of electrons, conduction electrons, which can move. So which surface charge distribution would cause the most electrons to want to move? Right? Because in equilibrium, nothing is moving. But you have to have non-equilibrium in order for charge to begin to move. Okay, so this now raises the next question, which is, well, there's a few different questions we can talk about, but one question would be, all right, well, if I turn the lights on and off in the class, the light switch is pretty far away from the lights themselves. Why does it go on sort of instantaneously versus it happens very, very quickly, right?
I know the answer.
Yes.
It's not the same electrons that are moving to there. It's like electrons here like pushing other electrons.
Exactly. So when you flip the switch, it's almost as if there's a pulse or a wave like a wave in the electric field that then causes all of them to push. Right? So that wave can actually propagate near the speed of light. Right? So that wire from the switch to the light bulb is already full of electrons, and now when the when the voltage difference, when the switch is closed, the electrons begin to be pushed, and they start to move. All right, so then let's look at the other question is, we discharged a capacitor there, and you might have noticed that the capacitor sparked. Yes, Carson.
Would there be an appreciable difference if the electrons actually did move all the way across? The electrons move kind of fast.
And do electrons move fast?
I mean, at least in some circumstances.
In what circumstances do they move fast?
Yeah.
So orbiting around an atom.
So orbiting around an atom, well, that's a more complicated question there. We could say they don't really move in an atom, but they do move when you try to find them. All right, so now, but we looked at individual electrons kind of moving freely through space, right? We looked at individual electrons moving through space in an electric field, and you can accelerate an electron rather quickly if it has no sort of impedance to its flow, right? So in this case, it turns out that electrons move rather slowly when we look at a typical conventional conductor. Right? Imagine turning the faucet on to your hose. Now, if your hose is already full of water, water starts coming out the end right away, but how quickly, the question we're asking is how quickly do the individual water molecules themselves move? So for a conventional conductor, we would want to picture a sort of a lattice of positive ion cores. And then the conduction electrons are free to move. These are conduction electrons. They're not necessarily bound by any particular ion, right? But now we have a non-uniform surface charge distribution, so we're going to have an electric field. Okay? So electric field looks like this. Now, which direction would the electrons want to move? They want to move to the right here. They want to move against the electric field. So let's just say, to start with, an electron was moving sort of with an arbitrary direction. Now, as it begins to move, it's going to follow these nice parabolic trajectories. Right. But then it's going to come to these scattering centers and be deflected. Now, over time, the electron will slowly start to drift over to the right. But there's all these collisions that are taking place as it moves along, which really slows it down. Right? And then if we consider the fact that this background core of positive ions, they're not static either. They're sort of vibrating at a finite temperature, so their effective size is larger. So imagine electrons trying to fall through a lattice core when there's a bunch of scattering sites that are impeding the motion of the charge. Now, what's happening here is you will notice that the lattice is actually vibrating a little bit as the electrons tumble their way through. So if I try to push too many electrons through the wire, it's going to really cause that wire to heat up a lot. So here I have a nice piece of nichrome wire under tension, and I'll take a piece of paper, hopefully. Let's see. Well, now what I'm going to do is turn on a power supply and drive current through this piece of wire. And if you watch the wire, slowly it starts to glow more and more. And now it's red hot. I wouldn't want to touch it at this point. All right, I could try to write my name, right? I didn't spell very well there. Right, and you can, now, so why is the wire getting so hot here? Yes?
There's a lot of collisions.
A lot of collisions. As the electrons move through, they're really causing the lattice to really vibrate quite a bit. So if you try to push too much current through there, it causes the, you start to see a lot of, it starts to get really, really hot, basically. Right, so that's why we have fuses in regular circuits, and to limit the amount of current that actually flows. Okay, so there's something called the, if we talk about something that's typical here, it's typical for copper, we would have what's a drift velocity of about 0.1 millimeters per second, a time between collision on the order of 10 to the minus 14 seconds, and an electric field about 1/100th of a volt per meter. So we have a really small electric field in a wire. You have 10 to the 14, well, you have 10 to the 14 collisions per second, and then you have a drift speed of about 0.1 millimeters per second. Right? So a huge number of collisions, and they're not really making their way very far through. Now, we can write down a formula for the drift speed. What sort of things should the drift speed depend on?
What is the drift speed?
The drift speed is the drift speed is basically the average velocity of the electron. If you were to average its velocity over time, sometimes it's going forward, sometimes it's going backwards, but because there's an electric field to the left, it tends to want to drift to the right over time. So the electrons are drifting over to the right. Right? And the drift speed is the average velocity. Right? Well, that drift speed should depend, if there's no electric field, there's no net preferential way that electrons would want to drift. They could equally as well drift either way. So it should depend on the electric field. So what I'm going to give you here is a model for conventional conductors. Should depend on the electric field. Other things that it should depend on is the charge of the electron, because if I have more charge, the electric field would affect it more, and it should have a larger drift speed. Right? Let's say each electron held twice as much charge, or it was some other ion that was moving, the drift speed would be larger. And the other thing it should depend on is, well, tau, the average time between collisions. Now, if tau gets larger, would you think that the drift speed should go up or down? It should go up, right? Because the collisions are basically less frequent. And then finally, the mass. Right? Larger mass means that it's going to accelerate not as quickly, not basically speed up as quickly. So the electron is actually never moving at a constant speed in this model. Right, this is a very simplistic model. It's never moving at a constant speed. It's always, there's scattering centers. And then we know in the presence of an electric field it's accelerating. Right? But here would be a model for a conventional conductor, which turns out to work pretty well for this drift speed. Right, now we can talk about what's called the electron current. Okay, and the electron current, which I give a little I sub e, is just the number of electrons passing the wire per unit time. Question?
So how would you determine the tau? If you were is it just like a constant that every material has, or is there a way to figure it out based on the density of the material, or what is?
Ooh, that's a great question. How would you determine tau? Well, now you could model different materials. So this is a field called solid state physics. And tau, given the lattice structure and the availability of valence electrons, you could come up with a model for how tau might be dependent on temperature, how it might be dependent on density, things like this, and the exact geometric lattice structure of the material. Right, but in general, I mean, how would you measure it experimentally? Well, I don't know. I'm sure there's a way to do it. Conventional conductors are pretty well understood, right? In terms of, why do we make things like copper? Well, copper is just a very good conductor. Now, I don't know how this number was measured. This number in particular, right? Now, more because I'm a theoretician. I don't do too many experiments, but you know, but you can create a model and then from there basically determine. Well, anyways, so this is some parameter here, right? But the point is that it's going to be different for different materials, right? And the only point I want to make here is that tau is very, very small for most conductors. Very, very, very small. It's sort of like the number of collisions per second that are happening in the air. It's a huge number of collisions per second that are taking place. Excellent question. Okay, so yes.
So tau is the number of collisions per second? Is that
Tau is basically the time between collisions.
time between collisions?
So about 10 to the minus 14 seconds.
Is that a 14 or an 8?
No, that's a 14. Yeah, tau is about 10 to the minus 14 seconds per collision. So that means every second there's about 10 to the 14 collisions. Yes?
That would be a given, right? Like you would give that to
You'd have to look that up for a particular material. Yeah. Okay, and right now, current, there's different kinds of current. Current is just flowing charge. The number of charge flowing past a point or unit time. So if I was to take this wire and kind of slice it like this, I could ask myself how many electrons pass that point in a given amount of time. And that's what we call electron current. Now, there's different kinds of currents, right? But for conductors, it's the electrons that are actually moving. Now, you can ask the question, how do we know it's the electrons that are moving, right? And that's more of a, that is something that I've just told you in this class, right? But there's experiments you can do to actually show that it's actually the electrons that are moving versus some other charge. Right now, you're just kind of taking that, you're just kind of accepting that on faith, basically, right? But you can do experiments to actually show that in conductors, it's the electrons that are actually moving. Now, the electron current depends on a few different factors: n sub b, a, and the drift velocity. N sub b is the density of electrons, the number per unit volume. A is the cross-sectional area of the wire, and v is the drift velocity. So all of these factors combined, you can think, all right, well, I'm going to have more current if I have a larger drift velocity. I'm also going to have more current if the wire is thicker and if they're more densely packed. The connection electrons, yes.
Can you say anything what the difference between the capital and lowercase numbers? In that equation, the electron current.
The lowercase a? Oh, density.
And what's the uppercase N?
This is the number density, and big N is total number. Right, and just to remind you, let's take a look here. So just to remind you, all the notes are on Polylearn. So let's look through here. So here we're at the drift velocity and electron current. All right, so those are up there. All the notes for the quarter are up there for you to check back on at any time throughout the quarter. And then also too, I do put lectures on Polylearn. So if you want to go back to a particular spot, you can say, all right, well, I want to see what the Faraday cage. Forget what the Faraday cage or something like this. You can go and just try to look it up as well. But yeah, so definitely that's just a reminder here All right, so electron current. Yes, Carson.
What's the units for that?
Electron current.
Yeah.
Well, electron current is just number inverse seconds.
So it'd be like a frequency?
Well, it's a current, right? So it has the same units as 1/seconds, but it wouldn't be interpreted as a frequency because it's a steady flow. Yes.
Is the density a density per volume or a density per area?
Per volume. All right, now there's another kind of current. So electron, so we have electron current, right? But electrons are not the only type of current. If I was to take if I was to build a simple circuit here where what I have is a light bulb, and I plug the light bulb in, it's not glowing because the two electrodes, there's no way for them to talk to each other. Right, but if I put water in the two electrodes, oops, that's going to take too long. Put some deionized water. Still, nothing's happening. So why deionized water? Because there's no ions. Now, what if I dissolve some salt? Still nothing's happening. What if does anyone have a pencil? All right, throw it up here. Toss it. Oh, there we go. All right, so. Right now, when the salt, the sodium and the chloride, the Na plus and the Cl minus dissolve, now we actually have conduction. And the charge carriers here, we have current in the solution. Thank you very much. But there's no, it's not the electrons that are moving, right? It's actually the ions. It's the sodium ions and the chloride. So current doesn't have to be electron current. But for conductors, we're dealing with electrons that are moving. But they're more invisible. We can't see them. Just like we can't see the sodium and the chloride move here. But if we were to let this run long enough, eventually you'd get a buildup on either of the electrodes as you'd get ions kind of drifting one direction there. All right. So this is electron current. Okay, let's just try a practice problem. Which of these 4 wires has the largest electron current? Take a moment to prepare your vote individually. The V here is indicating drift velocity. All right, prepare your vote. And on the count of 3, let's show our votes here. 3, 2, 1. All right, so take a moment to explain to your neighbor which one's the greatest, and then I want you to rank them, greatest to least.
Yeah, no, I see what you're saying.
Okay, so which one would you say has the smallest amount of current? Give you 15 seconds to prepare your vote. Smallest amount of electron current. I am seeing D. So we have D is the least. C is the greatest. Which one would be next? B. Then A. Right, and we're assuming here, what are we assuming here in answering this question? Yeah, we're assuming it's the same type of wire. We're not using nichrome versus copper versus aluminum or some, we're not using some different material. They're all made of the same material here. So this number, which is going to be material dependent, is the same. So the only thing that then matters is how fast are they moving and how much area do they have to move through. Right, notice the area, the rate, well, the most important point here is just to notice that, well, the area is proportional to the square of the radius. Okay, so this is electron current. Now what about ordinary conventional current? Ordinary conventional current is actually related to electron current. So big I, so now we're talking conventional current. Conventional current I is basically just going to be the electron current multiplied by how much charge is actually flowing, the charge of the electron itself. So that then just equals E n sub E A V D. Right, now we can also define something which is called the current density. And the current density, we give the symbol J, is I divided by A. So this is E n sub E V sub D. Which, if I plug in what the drift velocity is for our model here, this is not a law, by the way. This is a model. Right? It's not like Newton's second law. It's a model for conventional conductors. If I plug in V sub D, right, just plug that into there, I get n sub E, E squared tau over m, all multiplied by the electric field. Now, this term in the bracket we call sigma the conductivity. So we can write this as sigma E, which is actually what's called Ohm's law. Now, by the way, this is not, so again, Ohm's law, not all materials are ohmic, meaning that the current density is proportional to the electric field. Right? I mean, you could, in principle, have any relation. You could have J proportional to E squared, or something not even so simple in terms of algebraically. All right, now, final demonstration here, and then at the end of class, you're going to turn in your homework, and you're also, I'm going to put the midterm back for you to. You can pick up your midterm as well. I'm going to put the midterm, I'll clear some space here, and then you can pick up your midterm. But here I have a light bulb. And as soon as I close the switch, the light bulb begins to glow. And it's fairly bright. Now, one of the ways I could change the brightness of the light bulb is, here I have it wired through a tungsten filament. If I heat the tungsten filament, do you think the light bulb is going to get brighter or dimmer? When I heat the filament, it gets brighter, or sorry, it gets dimmer. When it cools down, it gets hotter again. So how do we understand that? Resistivity is increased. The current is decreasing, the light bulb is less bright. Midterm, I will put right here for you to pick up. If you could make a pile for the homework, and let's do that at the, yeah, let's do homework on the chair over here. Yeah, put your homework on the chair right here. Current is, yes, is the direction matter. All right, so let me actually, I'm going to clear some space.
It's gonna be shitty because after I take the final, like, I'm not gonna know if I pass the class or not. So there's no curve.
No curve.
What is the average? What was the average?
I don't know the average.
What?
Homework, you turn it in the chair. Midterm, that's front table chair. Okay, try.
Guess I'm just gonna start.
It's in New Mexico.
Oh my god.
I don't know if you took it.
I got a 0. I got a 0. No, I'm gonna have it in this one, but I got one of
So, what is you guys? That's oh, that's pretty good. Look at you, bro. 7%.
don't even
You're in the crew.
I don't know how.
You got a 29? I don't know how. Oh my god. I think you actually passed, dude. Dude, that's a 72.
Study, bro.
I know the average. Yeah.
Did you even grade the flat? That's the highest. No mark. I didn't solve any.
Me neither.
More than 50%.
Highest was a 30. No, not me, no. I wish. I didn't get any of the graphs. No, I did this so fast. Because I was like at the end. I did like 4 rounds. That's why. I got a 60. I got this. Calculated about a 16. What was it on? 40. I think I got 100. I just didn't get on.
Bro, who got the third?
Why are they 62? Why are they just gonna put? They just put like a 7 on the back.
Questions that have asked.
I asked.
I'm gonna ask one.
So I don't have those ahead of time, otherwise I would.
wrong. It's an infinity for the first one. I'll see you around. Good question.
I gotta move out of here for the next class.
Okay. I'll talk to you later.